Alright, welcome back. Digital Electronics. We are going to be going through lecture 16, doing AOI logic analysis. Alright, so what's that really mean? What we're going to do is we're going to take a circuit. Alright, so I'm going to give you a simple AOI, right, and or an inverter circuit. And we're going to determine the truth table based on the logic expression that comes out of that circuit. Okay, so we're able to determine the circuit's intended function from that. We're also able to check and make sure the circuit is working correctly. Okay, so we have two different analysis techniques that we've done. So we can go from a truth table to the equation technique, which is what we did last lecture, right? We figured out what all the minterms were, all right, and then from the minterms we created a sum of products. Okay, so that's the truth table to equation technique. Now we're going to go equation to truth table. So we're going to go the other direction now. But first you're going to have to come up with the equation from the given logic circuit. Alright, so I'm going to give you a circuit. You're going to come up with the expression based on the inputs going through all the logic gates and finally going through the last OR gate or AND gate or whatever we end up with, and get the logic expression. Based on the logic expression, you're going to be able to derive the truth table. Okay, so make sure you pause the video, write down all these different steps. Alright, if you do these steps, you will be very successful in going through this process. Alright, so I'm just going to kind of read them off so you can go through this as we want. We're going to add test points at every output of every gate. So I've done one like this on the board for you, so you should be familiar with this. This should ring some bells. We're going to add a column to the truth table for every test point. Now this you don't have to do all the time. You should be able to kind of recognize as we go through. But on the board I mark it and erase it. This might be a technique that you want to use, but it can get quite large on your paper if you're doing it this way. But you'll see what I'm talking about here in the next few slides. Alright, so we're going to work from the inputs to the outputs, and we're going to complete a truth table. So remember, your truth table, you have to have the right number of inputs, all right, and what the outputs are going to be from it. So from the completed truth table, we're going to identify the minterms from there, okay, but we're going to go from the expression to identifying the minterms. So before, in the last lecture, I gave you the truth table, and wherever the output was a 1, okay, you were able to identify the minterm. Now we're going to take the minterm and go back to the table and put a 1 there, all right. So we're going to use the extracted minterms to write the sum of products logic expression there. So we're going to take a basic circuit like this. And we've done this before when we kind of did one of our first breadboarding techniques using the AND gate, the OR gate, and the inverter when we did this. So we're going to derive the truth table for this based on this circuit here. So let's just take a look and make sure you pause the video, take the time to draw the circuit in your notes, okay, so that you can pass the lecture note quiz and that sort of thing. Okay, so we have three inputs, X, Y, and Z. X, Y, and Z, so we have three inputs. Alright, and then we have what? X has to go through an inverter and then into an AND gate, and it ANDs with a Y, and then goes into another AND gate. Z goes into that same AND gate. Alright, remember, read these left to right, okay, and then looks like Y is going to get inverted with X, and then go into an AND gate. And those last two AND gates go into an OR gate. So it'll make sense kind of as we go through the test points here. So remember, the test points are going to be, at the outputs of the gates, or where something, changes. So when we do this, all the test points are going to be at the outputs as you see here. So you can mark this on your circuit. So what I like to do is you're going to go left to right, top to bottom. So that's why TP is for test point. So that way you have an organized kind of methodology to do it. Could you go like test point 1 and then make test point 4 test point 1? Yes, you could. But try to have some sort of method and organization to it. So in this case, left to right, top to bottom for our test points. So we can see clearly where test point 1, test point 2, test point 3 are, and test point 4, test point 5. So outside of every logic gate, there's a test point, and then F1 is kind of our last test point, but that's everything, coming together as we go through the truth table here. Okay, so we can make a table here that's going to look similar to this. Okay, So you can copy this table down, but we're going to walk through it. So how do we know how to make this? Well, we have X, Y, and Z, right? Those are the inputs looking back at the circuit right here. And then we have our output, which is F1. And then we write down what the value is at that test point. All right, so at test point 1, what happens if I put in a 0, 0, 0? All right, well, test point 1, if I put in a 0, okay, for X, what should come out? Or we should get a 1. Does that make sense? Because a 0 going into that inverter kicks out a 1. The only thing that's going in as a 0 is X equals 0. And the inverter changes it to a 1. So that's why our test point at test point 1 is a 1. Then we look at test point 2. All right. So we have a 1 going in from test point 1, and we have a 0 going in from Y. So a 1 and a 0 is 0. So test point 2 should be a 0. All right. And I'm going across the very first row here where we have the inputs 0, 0, 0. You're going to do this for every single input. Okay, I'm just going to kind of walk you through this one. So test point 2, the output is a 0. All right. Then test point 3, we have a 0 from test point 2 going into the AND gate, and we have a 0 from Z going into the AND gate. So 0 and 0 produces a 0. So test point 3 is a 0. Okay? And then we're going to let's take a look at test point 4. We're sending in a 0 from the Y into the inverter. The output of the inverter is a 1. So test point 4 should produce a 1. Okay? And then we need to find test point 5. Test point 5 is coming out of that AND gate. Into that AND gate is a 1 and a 0. 1 and 0 is 0. So test point 5 should be a 0. All right, and then lastly, we can get what F1 is by ORing test point 3 and test point 5. So if we go back to our table, all right, test point 3 is a 0, test point 5 is a 0. So 0 or 0 produces a 0, so F1 will be a 0 in that case. So you're going to kind of walk through, each scenario based on this circuit here as you go through that. So I've kind of guided you through step by step, but now we would do it with 0, 0, 1, where X is 0, Y is 0, and Z is 1. And you would do the same thing and fill in this truth table here. I've given it to you, but I want you to kind of verify and go through it. So, after you complete all the test points, the focus is here. The focus is when is F1 equal to a 1? Alright, so there's 3 separate locations here. There's when X is 0, Y is 1, Z is 1. There's when X is 1, Y is 0, Z is 0. And there's when X is 1, Y is 0, Z is 1. Those are my 3 ones. Okay? So, with that, I can write the minterms. Not X, Y, and Z. Or I could say X bar, Y, and Z. Alright? Then I would have X, not Y, not Z. Then I would have X, not Y, Z. So I would be able to write my 3 minterms, alright, and write my expression for F1 using the truth table. Now you could have done that, just by using the letters X, Y, and Z on the circuit instead of using zeros and ones, okay? Same kind of concept. But remember, so I'm stepping back here. Let's look at that first point in the truth table where F1 is a 1. 0, 1, 1. I just want you to remember how to write the minterm out correctly. Remember, it's written as X bar or not X because the X value is 0, and there's a Y and a Z. Both of those are 1s, so that's why there's no bar above them. Okay, so since it's a 0, 1, 1, that's why we have X bar, Y, Z. Remember, the other way to say that is not X, Y, and Z. All right, same goes with the other two. And then write it out as one expression. All right, so let's do this as an example. Why don't you pause the video, give this one a shot. So draw this circuit down, okay, and then see if you can recreate it. Doing the same thing. Create the truth table, all right, and fill in all the test points. So you should have 1, 2, 3, 4, 5, 6 test points, okay? in this case. One after every single gate. One after every gate. Okay, and we see there's 6 gates. All right, now technically F2 is your last test point, so you can do one, there should be a test point before that first inverter, and then the 2 AND gates, so those 3 test points, and then 2 test points on the bottom. You don't need the other test points, so you could go with 5 test points. Or if you went with 6, 6 would be the same as what F2 is. Alright, so draw the circuit, and I want you to see if you can develop the truth table. Now remember, when you do this for A, B, and C, it still goes 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way up to 1, 1, 1. So that part doesn't change. It's just you need to go through the analysis piece, all right, and check out all your test points. Okay. So here is the solution. I want you to be able to check yourself. Okay, so you should be able to go through each test point and see what the output is. All right, if we're sending it through an inverter, if it was 1, it becomes a 0. If it's a 0, it becomes a 1. All right, and then we send it through the AND gates. So you should see how to develop the minterms. Okay, this slide's fairly self-explanatory. So we're really just analyzing every single test point. Okay, and based on those test points, it's going to help us determine when F2 has a 1. All right, F2 can only be a 1, right? If one of those, if test point 3 is a 1, test point 5 is a 1, or both of them are 1s at the same time. If test point 3 and test point 5 are 0s, okay, you will not have an output of a 1. So there's 3 scenarios where this occurs: 0, 1, 0, 0, 1, 1, and there is 1, 1, 0. Remember, 0, 1, 0 translates into X bar, Y, Z bar, or not X, Y, and not Z. All right. Then we have 0, 1, 1, that translates to X bar, Y, Z, and 1, 1, 0 translates to X, Y, Z bar. And then we write it as a sum of products, so you can see at the bottom what the sum of products is. Okay. So, process. Work from the inputs to the outputs. Write the cumulating logic expression at the end. Use the circuit's output logic expression to derive the circuit's truth table. Okay, so let's do it a little bit different way here. Okay, we're going to draw the same circuit out. Okay, this is the first circuit we worked with. So now, instead of testing every single point, 0, 0, 0, all the way up to 1, 1, 1, and writing out all the test points, what we can do is kind of send the variable through now. When we send the variable through, it makes it a little easier and less work. And what do we end up with? Okay, a much simpler circuit. Okay, when we did this the first time using the truth table, we had 3 different sum of products that were all 3 inputs. That's condensed down to these 2. So the difference here is, instead of testing points using 0s and 1s and going through the entire table this way, we're able to put the variable through. And what does that mean? So let's take a look here. If we put X through the inverter, we get what? X bar. We get not X out of that. Okay, remember, the inverter is a NOT gate. So when we put X in, we get not X out. Then what? That not X gets ANDed with Y. So we write that as not X and Y. And that goes into another AND gate, and that gets ANDed with the Z. So the output of that AND gate is not X and Y and Z. So I can write that, that's a product, right? X bar, Y, Z. Or I can say it is not X, Y, and Z. That's going to go into the OR gate with the other expression. The other expression, we're sending Y into the NOT gate, so we get out not Y. And that's ANDed with X, so we get X, not Y. That goes into the OR gate. Remember, the OR is our sum, so we get our final expression as F1 is equal to not X, Y, and Z, or X, not Y. Now, how does that help us out? That simplifies our expression and makes our truth table a little easier. So now we write out this long truth table, okay, and the only place that we're going to have 1s is when we have what? Not X, Y, and Z, so 0, 1, 1. Here's the other part we got to pay attention to. Just because it says X, not Y, it occurs every single time there's an X, not Y. We don't care if Z is a 1 or a 0. So when we do this, all right, our truth table ends up like this. We took our expression, all right, X bar, Y, Z, or X, not Y. All right, so we were able to find the first min term and put it into the truth table. So we put a 1 next to 0, 1, 1 for our output F1. And then I said anytime we have X, not Y, which means we're looking for a 1, 0, and then we don't care if Z is 0 or if Z is 1. So we can put an output of 1 when we have 1, 0, 0, or we have the condition 1, 0, 1, as shown here on the truth table. Those are our only 3 outputs where it is true. Now, you only place the 1s, and we fill the rest in with 0s. Hopefully, it's starting to sink in here. We are going to be doing multiple homework problems doing this so we get good at it. All right, so we should be able to either go through, use all the test points, fill out a really large table, or we should be able to send the variables through, and based on what gates they go through, whether we're ANDing, which is shown by multiplying, inverting, showing with the bar, or ORing, showing with the plus. Okay? Next, I want you guys to try this one. This was the second one we did, okay? So you already kind of know what the answers should be. We're just using the second method. So we're, instead of going, sending all the 0s and 1s through, we're going to send the variables through. Keep in mind the variables now are A, B, and C, not X, Y, and Z. So I want you to draw this circuit again, and I want you on your circuit to mark the test points, but you're not marking the test points necessarily, you're just putting what comes out of the logic gate. Is it A or A bar? Is it B or B bar? Are they ANDed? So is it AB or is it A not B sort of thing? Okay, like we just did in the last example. So go ahead and pause the video, and then I'm going to move forward with the answers. All right, moving forward now. So what you should have gotten was this. All right, we send A through the inverter and we get not A back, and then that's ANDed with B. So we have not A and B going into another AND gate. So we have not A and B going into that other AND gate, and that's ANDed with C. So we end up with not A, B, and C. Okay, next, I'm going down below here real quick. I'm not going into that last OR gate yet. We're going to send C through an inverter. So when we send C through an inverter, we get not C, and that ends up being ANDed with B. So the output of the AND gate is B, not C, and then that's going into the OR gate. So our final expression is not A, B, and C, or B and not C. Simplified expression. Okay, so the first min term that you should fill in, you should have your truth table. You should have your A, B, C, all those filled in, 0, 0, 0 through 1, 1, 1. Okay, your F2 should be blank still. Okay, well, you've completed it, so hopefully it matches what I have. But when you're doing these normally, okay? So when we have not A, B, and C, so that means 0, 1, 1 for my inputs. When I have 0, 1, 1 in that specific order, my output is a 1, so F2 should have a 1 right there. Then, look at that second expression. We have B, not C. It means we don't care about what A is. We don't care if A is a 1 or a 0. So it's going to handle all the cases where we have B being a 1 and C being a 0. So that happens twice. That happens at 0, 1, 0, right? That's where A is 0, and we don't care about A. We just care that B has to be 1 and C has to be 0. So we put a 1 there. And then if we look at the next one, all right, we have 1, 1, 0. That's where A is a 1. We don't really care about A though, but B is a 1 and C is a 0. That has to hold true. So there are 3 points here where we have outputs that are true for the truth table, and then you put 0s in for the rest of them. So hopefully you're getting the point here. And like I said, we've done a few of these in class. So hopefully this rings a bell for you as you do some of these. All right, so once again, we might do 1 or 2 more different ones on the board in class. Make sure that you have good notes for this for your lecture quiz. If you have any questions, feel free to shoot me an email or ask in class. All right. Else, guys, end of the lecture. I will see you guys in class and in lab, and we'll move forward and get through this piece, and then eventually we're going to do all this and do some breadboarding out of it. All right, guys, have a great day. We'll see you soon.